Hey, welcome back to Short Text 331. Today we are going to talk about Gaussian integrals and Feynman trick. This Feynman trick is a very famous trick, and we will use it today to calculate some integrals. In the previous video, we saw that this Gaussian integral that I called I0 of lambda, which is given by the integral from minus infinity to infinity of e to the minus lambda x squared dx, is equal to square root of pi over lambda, assuming lambda is greater than 0. And this can be extended to other cases of lambda, but for now, let's assume that lambda is a real number and it's greater than 0. And so this is a classic Gaussian integral that you will see many times. And if we had lambda equal to 1, of course, it's just square root of pi, and that will be part of our work today, deriving that result. And we argued that this result can be used to calculate higher, more complicated integrals of this shape. So the usual Gaussian integral, but also with the monomial factor here, x to the 2n. And I should say that in passing that, of course, if you had an odd power here of x, then you would have the product of an odd function with an even function and a symmetric interval. So that integral is 0. We don't even have to worry about that. And so we only care about the even powers, x to the 2n. So we saw that if you take a derivative with respect to lambda of this I0 of lambda up here, then down from the exponent comes a minus x squared factor. Remember, this is derivative with respect to lambda, not x squared. You cannot take a derivative with respect to x because x is used as a dummy variable here in the integration. And so we don't have to worry about that. But down comes from the exponent a minus x squared. And so that basically tells you that by taking one derivative with respect to lambda, you have access to the n equals 1 case. Okay, and so if I flip the sign of that derivative, putting this sign on the other side of the equation if you want, we have that minus differentiation with respect to lambda of I0 of lambda gives us I1 when we set lambda equal to 1. That's what we call I1 in this equation. If we intend to keep the lambda up here to evaluate at lambda equal to 2 or 3 or pi or whatever you want, that's also possible. You just leave it and you don't set it to 1. But in our case, we're interested in the case where this coefficient up here is 1, and so that gives us the result of taking that derivative. And if you go ahead up here and you take that derivative with respect to lambda, you find that the resulting integral is square root of pi divided by 2. That's all there is. It's very simple. In other words, we take the derivative of both sides of this equation. On the left, you pull down a minus x squared each time you take a derivative, and on the right, you deal with the powers of lambda here, which are going to be minus 1/2, minus 3/2, and so on and so forth. Every time you take a derivative, that keeps going more and more negative, and then you set lambda equal to 1, and you see what you get at the end. And for a single derivative, that's just square root of pi over 2. Now, as I was saying, you could take more derivatives to generate all the in you want. The one thing you have to be careful about is that, for example, if you take two derivatives, then you're going to get two minus signs, and they will cancel each other out. And so there's a minus 1 to the n here that you have to account for to be careful, or to account for the effect on the odd cases, the odd n. Okay, so by the way, don't confuse odd n with odd exponent here. Odd n still makes it 2n an even number. In any case, now the main problem we have is, how do we determine this? How do we determine that I0 of lambda is square root of pi over lambda? If we start with I0 of lambda, then we have the integral from minus infinity to infinity of e to the minus lambda x squared dx. And the first thing you can do is to absorb lambda into x. You can absorb lambda into x because lambda appears only here and down here. And what that will do is it will turn this integral, where the parameter is mixed up with the integration variable, into two factors. One factor is just the integral over some variable t and nothing else, and then the parameter has been extracted out here, out of the integral, 1 over square root of lambda. And you can see how that works out, because this is square root of lambda squared, and that turns into t up here squared, and then you turn the dx into a dt, and you pay the price of 1 over square root of lambda by this equation, and that's really all there is. And so in this case, we already know that the lambda dependence of this integral is always going to be 1 over square root of lambda, and now we have to calculate this guy. So that's nice. That's a step forward. So we're going to focus then on this result. At this point, I want to say that this series is meant for my students at the University of North Carolina, Chapel Hill. If you find this series helpful, regardless of whether you're a student or not, please consider liking these videos and subscribing to the channel, as that would really help us. Now, if you're not a UNC student and you're looking for a tutor in physics or math, either in English or in Spanish, I can probably help you. So you can contact me at shorttext331@gmail.com, or you can leave a message in the comment section below. So let's see how we do this integral then. And the trick is a classic one, and you might have seen it before. This integral from -infinity to infinity of this Gaussian factor is calculated by first squaring the integral. This is a really weird way to proceed, to really square the integral that you want to calculate, but it actually helps. And the reason it helps is that by taking the square of such a nice function as this Gaussian, we're allowed to rewrite it as an integral over the whole real plane of r squared. So we're going to imagine that this t and v that I use here as dummy variables for the integrals are actually the x and y coordinates, if you want, of this plane R2. And so joining the integrals and the integrands, we get e to the minus t squared plus v squared dt dv. And by that rationale, following that line of development, we have t squared plus v squared is our radius squared, and this, again, in this plane, where one is t and the other one is v, if you want. And dt dv is r d phi, and phi is our angle on that plane. And so this integral then takes the form e to the minus r squared r dr d phi, and we're integrating over the whole plane just because our integrals go from -infinity to infinity, so we're integrating over the whole plane. And by the way, if the integrals were finite, this would be much harder. The fact that we're integrating over the whole plane, in fact, really helps a lot. And so we have the integral over phi and the integral over r. The integral over phi is something we can do right away because there's no phi dependence in this integrand, and so that's going to give us a 2 pi. The other integral over dr is an integral from 0 to infinity, e to the minus r squared r dr, but now we're in much better shape than before. And this is really the main reason why one does this trick, that if we want to do an integral of a pure Gaussian, then we don't have a t here that would help us change variables from t squared to x or whatever you want to call it. But now we can do that. We can play that game, and so we can multiply by 2 and divide by 2 elsewhere, and turn this 2r into the derivative of r squared. And that helps you directly to find out that not only do you have this factor of 2 pi coming from the angular part, but the radial integral can be done right away, and the result is 1/2. And as a result, then 1/2 times 2 pi is pi, and that's the result of our integral squared. Remember, we squared the integral, and the result is pi. That means that one of the integrals is square root of pi. And so that's how we get to the I0 of lambda result being square root of pi divided by lambda, or square root of pi over lambda. Okay, remember that the dependence on lambda came directly just by replacing variables in this way. T is square root of lambda x in our original integral, and so that's pretty straightforward, that part. And we only need to calculate the square root of pi factor, and this is how you do it. This is the classic trick. And so once you know it, then you may or may not use it again. This is a very specific trick for this integral, and but now that you know this one, then you can move on and calculate other integrals. There are other cases where Feynman's trick is possible, and it's useful, and it can help you calculate integrals very quickly. And the two principles guiding how to apply this trick are as follows. First, we must be able to insert a parameter such as lambda, we did here, in a clever spot, so that when we differentiate with respect to that parameter, we get the integrals that we want. Okay, that's very important. If you can't find a spot where you can pull down stuff from the exponent or somehow generate the integrands that you want, then you're not going to be able to apply this trick. But there's a second part, which is just as important, which is that the base case, the stuff that you differentiate, in our case is I0, must be an integral that we can solve analytically for all values of lambda, or at least for all values of lambda that matter to you, for the integral that you might be interested in. And so this is really important. If we're not able to do this part, solve that problem analytically, then we can't differentiate, and then you cannot make progress in that case. So it's not enough to just cleverly insert a parameter that will give you the integral that you want. If you cannot solve the base case analytically, then that being smart to insert a parameter doesn't really pay off. So let's do an example where things work, In fact, we're going to see a couple of examples where things work. I'm not going to show you an example of things that don't work, but you can easily come up with those yourself, probably. So let's consider then this integral that I call Jn, the integral between 0 and 1 of logarithm of x to the power n times x squared dx. And in principle, this is an integral that can be done in a variety of ways. We're going to see here that the Feynman trick actually helps you figure it out in a quick way, a relatively quick way, or a useful way. And this 1 here doesn't have to be 1, it could be a different end point. Same with this one. We'll see how those play a role. But a priori, just looking at this integral, it looks kind of daunting. There's a logarithm to the power n, that's really the difficult part. The x squared doesn't seem too terrifying, but the logarithm of x to the power of n for arbitrary n looks difficult. One way to solve it is to say, let me take y to be log of x, and so that means x squared is e to the 2y, and x is e to the y, and so dx is e to the y dy. And so we turn that integral into this. You can do the calculation, it becomes the integral from minus infinity to 0. So this becomes, the 0 becomes a minus infinity in these variables, the 1 becomes a 0 because of this transformation, and y to the n comes from the logarithm, and e to the 3y comes from x squared dx. And you can do that using usual methods. You can do this integral using integration by parts a bunch of times and so on, but we're going to do this in a more elegant way using this Feynman path, this Feynman idea. And for that purpose, we're going to rewrite x squared as e to the 2 log x. So this x squared is something we're going to write as e to the 2 logarithm of x. And so with that, we're going to define our base case, or j0 of lambda, as the integral from 0 to 1 of x to the lambda dx. And that's, if you recall, x to the lambda is something you can write as e to the lambda logarithm of x. You can always do that. So then we do that, the integral from 0 to 1 of e to the lambda logarithm of x dx. And this is an integral we can do easily. And so it's our base case, because this is something that we know very well how to do. It's just 1 over lambda plus 1, x to the lambda plus 1, evaluated between 0 and 1. And the result is 1 over lambda plus 1. It's very simple, very easy to do on one hand. And on the other hand, you can see from this form here that if you differentiate with respect to lambda a bunch of times, then you're going to pull down from the exponent logarithm of x to whatever power, order of differentiation you've applied. And so let's do that once and see what happens. So then if you take one derivative with respect to lambda of j0 of lambda, you're going to pull down from the exponent logarithm of x, and you're going to get the result for j1. Indeed, you get that integral, and on the other hand, you can differentiate this formula with respect to lambda once and evaluate at lambda at the lambda that you want. In our case, we want lambda equal to 2, and so if you do that, then you're going to get j1 on the left and j1 on the right, and so for lambda going to 2, and so you obtain that the integral from 0 to 1 logarithm of x squared dx is going to give us simply minus 1/3 squared, so minus 1/9. And so that's the result for one derivative, but you can take more derivatives and evaluate the result for any value of n. You see, because it's very simple to take derivatives with respect to lambda of this kind of object. So that's perhaps an extra property that some of our integrals will have, that when you manage to calculate j0 of lambda, it could very well be that it ends up being a very simple function of lambda that is easy to differentiate. And so in that case, then that's an extra benefit, that right away, just by executing simple differentiation, you can calculate very high orders of Jn in this particular case. So as an exercise, I want you to think about how to generalize the above result that we did for Jn to Jnm as two indices here, where we've added an extra index m to the power. Instead of being a square, now it's a power m. And in fact, you could imagine that this m could be any number. It doesn't have to be an integer, but suppose it's a positive number. So how would you work with the Feynman trick, or how do you generalize the Feynman trick that we just developed for Jn to this case Jnm? And with that, I will see you next time. Remember that this is serious meant for my students at UNC, but if you're not a UNC student and you're looking for a tutor in physics or math, in English or in Spanish, you can contact me at shorttext331@gmail.com, or you can leave a message in the comment section below. Otherwise, if you just enjoyed these videos and you like the channel, please consider liking the videos and subscribing. It will really help us. And that's it. That's all I have. Until next time.